Welcome everybody to today's Penn AI Tech webinar. Penn AI Tech is the Penn Artificial Intelligence and Technology Collaboratory for Healthy Aging, an initiative funded by the National Institute on Aging. Today, we're very happy to have Dr. Huang as our speaker. Dr. Huang is an assistant professor of pathology and laboratory medicine with a secondary appointment in the Department of Biostatistics, Epidemiology, and Informatics at the University of Pennsylvania Perelman School of Medicine. And after receiving a PhD in electrical and computer engineering from Purdue in August 2021, he completed his postdoctoral training at Stanford University from 21 to 24. Dr. Huang's research focuses on advancing AI and machine learning in medicine, including the development of vision language foundation models for pathology. Some of that work has been featured on the cover of Nature Medicine in 2023. Also interested in pathologist-AI collaboration, neurodegenerative disease research, as well as work on optimizing large language models. His work has been covered by the New York Times, Stanford Magazine, and Stanford Scope. I want to remind our audience that we'll have a Q&A at the end, but please feel free to use the Q&A feature to post any questions you have for our speaker, and we hopefully will be able to address them at the end of his talk. So without further ado, Dr. Huang, thank you so much for joining us today, and I'll hand it over to you.
That's great. Yeah, thank you so much for introducing me, and hope everyone can see my slides. So,
Yes.
Hello everyone. I'm Huang, assistant professor at Department of Pathology at the UPenn. And so my topic today is Agentic AI Framework for comprehensive medical imaging interpretation enabling laboratory intelligence. All right, so before we get started, I would like to briefly recap how the clinical workflow looks like. Typically, a subject will notice symptoms or undergo a screening process, such as imaging or blood test. And a primary care physician or specialist will identify an abnormal region and recommend diagnostic testing, such as biopsy or imaging. If a mass is found and if a biopsy is, the biopsy is usually done to determine whether it is a malignant or not. And if the tumor is small and accessible, surgical resection will be performed. And during the surgery, if a rapid diagnosis is needed, the pathologist will receive a frozen section for immediate analysis, such as assessing the malignancy, surgical margin, and lymph node metastasis. Staining such as immunohistochemistry. And here, the pathologist generates the pathology report after inspecting the whole slide image carefully. And that report usually includes the diagnostic information such as cancer types and tumor grade, margin, and so forth. Additionally, it's sometimes added with molecular testing, immunohistochemistry, or other advanced diagnostic techniques. And in the stage 6, oncologists are consulted for treatment recommendations, and the patient receives therapy and may have follow-up visits. So now you can see the subject's journey all the way from screening to become a patient and going through the follow-up visit through doctor, surgeon, pathologist, pathology reports, and back to the doctor, goes to the treatment recommendation and follow up with the patient therapy. So as you can see in this hospital clinical workflow, pathology is the medicine's ground truth for cancer diagnosis and treatment planning. So when pathologists are making a diagnosis, they will typically compare with known patterns, classify tumor types and tumor grade, measuring the tumor size and counting the mitotic figure, measuring the invasion length, and request molecular testing. So here you can see a typical pathology report look like. So the final diagnosis, for example, is invasive ductal carcinoma, moderately differentiated. And as you can see, some diagnoses are basically based on the inspecting global and local tissue structure, but sometimes it requires manual counting of the mitosis, plasma cell, neutrophils, which is very laborious, time-consuming, and subjective, and often associated with a higher inter-observer variability. But those measurements are also very important, and it is critical for determining tumor stage or tumor grade and aggressiveness of the therapy. So to overcome this problem, especially the accuracy and the agreement, we want to introduce a pathologist-AI collaboration framework for enhancing the diagnosis accuracy and efficiency. And for this, we developed the Nuclear I/O platform. So how does the Nuclear I/O platform help on this workflow? Well, after slides are getting digitally scanned, the platform can perform the nuclear segmentation and feature extraction. And we're able to extracting over 150 features, such as the 46 color features, morphology features, 32 textual features, 44 spatial features, and 32 additional pre-trained deep learning features. And after the pre-processing, every single cell will carry more than 150 features on this whole cell image. And so pathologists, they can easily visualize those cells and mark them as tumor, for example, or other cell types. And because all the features are pre-calculated, associated with every single cell, so then we can build a very simple classifier so that can be trained rapidly, and immediately after every single step of annotation by pathologists, we can see the model performance in real time. So the beauty of this human-in-the-loop active learning framework is that the clinicians, they can visually see the imperfect predictions, and we can easily correct them through subsequent annotation. So in this way, they can quickly establish a very accurate cell classifier to highlight the cells of their own interest. Okay, so now the question comes with, that seems very powerful to quickly adapt a classifier to tell us the cell of our own interest. So can we evaluate the impact of the human-AI collaboration in digital pathology? And what we really want to know is, will the expert with AI's assistance can perform better than manual inspection by the expert alone? To answer this question, we first investigated plasma cell identification in endometrium biopsy. So plasma cells look like this, are quite important for diagnosis, for diagnosing the chronic endometritis, which causes the infertility or the failure of pregnancy. But finding the plasma cell is extremely difficult and tedious. They are usually fewer than, let's say, usually fewer than 10 out of 1 million cells in a whole cell image. And often the time, their shape and colors are almost identical to other lymphocytes, unless you zoom into high power. When I say high power, it means like you have to zoom into very deep detail. And so finding the plasma cell is just like finding a needle in a haystack. It's super laborious, super tedious. And often the time, we just missed it. But through our Nuclear I/O platform, we enable a gallery where pathologists, they can click on every single individual cells that are prioritized by the probability. And they can easily click on every single cell and visualize and inspect them on the original whole slide image. So we invite 11 pathologists to inspecting 39 cases, basically 39 slides, and ask them to respond, is there any plasma cell exist, and how many are they? And do you still request CD138 to confirm your finding? Well, basically, CD138 can stain a brown color on the plasma cell, but it's not specific to plasma cell. It can also stain the brown color on the epithelial area. The final golden standard to call the plasma cell is still from the H&E. So our experiment found that across 11 pathologists inspecting 39 cases, using the AI to assist can double the sensitivity, greatly reduce the uncertainty by 69%, and reduce CD138 requests by 63%. So this suggests that using AI can make your diagnosis better. Additionally, people use AI assistant to took less than 80 seconds per slide, which is a total of a 62% time saving, and make your diagnosis faster. So keep in mind that plasma cell classifier was just annotated and trained by only 2 clinicians within 3 hours using Nuclear I/O active learning strategy. And the same strategy can also be applied to, for example, neutrophils, mitosis, and other cell types. Okay, so in the second analysis, we further investigated another interesting study, which is investigating colorectal cancer lymph node metastasis. So we invite 8 pathologists to look at 25 cases with a total of 138 lymph node whole cell images. Some of the whole cell image may contain multiple lymph nodes, and some of the lymph node may have a tumor metastasis. So we found that when pathologists inspecting the slides, AI can greatly improve the chance of detecting tumor cells, especially the isolated tumor cells. So for example, here, isolated tumor cells are a tiny cluster that are almost invisible at a low power unless you zoom into very high power. And it is really hard to find it in this snapshot. So without AI, it is nearly impossible to notice that. But with AI to highlighting that field, the pathologist's behavior were kind of like prompt to take a closer look into that area to avoid the missing or the mistakes. And that's how the AI can benefit us in clinical practice, right? So since we recorded all the user behavior, we found that the AI does change the pathologist's behavior in looking at the slide. The analysis showed that with the AI, clinicians save up to 33% of the time in ruling out the negative cases and 29% of the time in finding out the positive lymph nodes. And this suggests that AI can help clinicians in finding both single cells and clusters of tumors, and can help clinicians to not only improve the diagnosis and also reduce the time and change the way that they look at the slides. So while nuclear IO performs well in certain clinical scenarios, such as plasma cell classification, its generalizability across all the clinical tasks is still limited. So because nuclear IO is designed specifically for cell classification, and it follows a fixed workflow, all the way from nuclear segmentation, annotation through active learning, and classification, and then visualization. But in real research and practical research and clinical scenario, questions are much more diverse and complex. So therefore, a single platform may not be enough. For example, often the time in real clinical workflow, we sometimes will ask like, how many cells are in the tumor region of this breast cancer? Or what is the depth of invasion in this colon cancer image? We definitely need a better system to answer such high, diverse, variable questions. And that's why we need a language model to understand the question and find an appropriate tool to solve it, right? Without a language model, it is nearly impossible to interpret those questions. So, however, when you try sending these images into ChatGPT and ask like, how many glands in this area? Well, the ChatGPT is pretty smart. It understands what you're asking. And the ChatGPT will also generate a Python code using OpenCV library. And it helps you to execute those Python code and generate you the answer and help you visualize the answer. But unfortunately, ChatGPT does not provide accurate answers because the constructed pipeline is imperfect. And the code cannot accurately determine the different structures. And in this case, it will output like there are only 2 glands are detected, which in reality, there are over 20 glands in this area. So similarly, if you ask like, how many tumor cells in this area, ChatGPT is also pretend to be pretty smart and will segment all the cells. And with the answer estimated about 426 tumor cells. But when you take a closer look into the results, you will realize that the way that ChatGPT segment the cell is poor. And when you zoom in, you will understand that it's just not really the cell. It is a group of the cell. And so the number of 426 cells is imperfect, and it's actually incorrect. So why do those ChatGPT like vision language model fail in the medical imaging? So I kind of summarize into 4 different reasons. First of all, there's no workflow. End-to-end deep learning black box often hallucinate and limited the explanation from the model. And second is a domain knowledge. As we can see, ChatGPT was trying to use OpenCV library to understand the pathology problem. But OpenCV is an excellent tool for image analysis, but it's not really aligned towards the medical image. And there's a huge domain gap in here. Just because we have the domain knowledge gap, so the complex medical image analysis can be suboptimal. And that problem is both medical and technical. And third limitation is the agent experts limitation. Those tools, when they are calling, are not really tailored down to handle the medical related tasks. For example, when we are doing the image segmentation, such as the cell segmentation, we better use the latest state-of-the-art cell VIT to segment those cells in pathology images rather than using the OpenCV. And lastly, there's no user-friendly platform. Such complicated source code and compiling prevents the clinicians to easily use it, audit it, and improve it and adjust it. So given all those limitations, we understand that simple ChatGPT-like vision language model cannot help us to understand and answer all different type of questions. But to solve it, we have a solution. We propose TissueLab, which is a co-evolving agentic AI system that can run AI agent workflow for any type of research question and clinical tasks. So what does that mean to us? What is the agentic AI system and what is the co-evolving? Well, to answer the agentic AI system as a terminology, think of tools like Lego blocks. Tools such as segmentation model, object detection model, classifier, and encoder. These are all tools. And the large language model are like manual. It helps you to understand to what extent those tools are capable of doing what tasks. And it helps you to assemble those tools into a functional workflow or a functional machine that can help you to solve the actual problems in reality. And so that's how the agentic workflow, that's how I make an analogy of the agentic workflow. And in our TissueLab, we borrow this concept. We provide a big factory of Lego blocks or tools. Each tool has a well-documented guideline and input-output format. So the large language model knows under what condition, what scenario we should invoke them, we should call those tools, and under what condition we should assemble them into a functional workflow and into what order. For example, if the user asks like, can you help me to calculate the ratio of the tumor cell versus lymphocyte in this breast cancer tissue? Well, that typical question are sometimes really useful in both clinical diagnosis as well as medical research to help us understand the tumor immune microenvironment. So to answer this question, we have the entrance agent to initiate a workflow. And it looks up the tool factory, select the relevant model, and sort them by the dependencies. For example, the nuclei classification has to go after we finishing up the nuclei segmentation. So finally, TissueLab will generate the workflow and also generate the analysis code, and we can help you to execute the workflow automatically. And the final output, when we summarize the result, it will give you a natural language answer. Here, example will be, there are 52,000 tumor cells and 34,000 lymphocytes, and the ratio of tumor to lymphocytes within this cancerous region is 1.53. And this approach really avoid hallucination by building the structured pipeline. So let's see how the TissueLab agentic AI system can handle various of questions arise from the clinical and research setting. We primarily categorize them into 5 common question types. First is relational analysis with reasoning. Second is diagnostic reasoning with medical knowledge. And third is high-dimensional 3D, 4D image analysis. And fourth is co-evolution with human-in-the-loop annotation. And lastly is the multimodal fusion analysis. And now let's see how the TissueLab performs. So the first example is relational analysis with reasoning. And the question is, can you help me to calculate the depth of invasion for this column host line image? Which is a type of a typical distance measurement in pathology image. So once the user asks this question, the pipeline will automatically generate by the agent system. So this is a typical workflow that agent will generate. And the workflow will look up, the way the workflow was generated is by the agent, first look up all the agent tool factory, check the data container and for available data, and then plans the analysis. And after the patch classification is finished, the agent will inspect the data container, identify the patches that are classified as epithelium or the tumor, and generate the analysis code, the Python code to summarize analysis. Well, so sometimes our code may generate bugs because the underlying language model behind it we're using is GPT-4o by the time we're developing this workflow, this agent tool. So sometimes it can make the mistakes, but when it makes the mistakes, we will try to execute it and understand what is the error, and then the agent can regenerate the code until we can really run and get a real answer correctly. So it will then eventually calculate the depth of invasion from the visible plane in the section. It is pretty smart. It will understand how to measure the distance from every single tumor patch to the nearest border, and then find a maximum value among all these distance measurements. And the code will read the intermediate results from those tools, and then try to assemble them through the analysis. And the answer here will give you directly the depth of invasion in this column section is 1.3 centimeter. So we conducted a comprehensive experiment on multiple slides measuring the depth of invasion, and we also compared those recent ChatGPT and other vision language models such as Lava, Llama, and even GPT-5 Vision. And we found that our performance is much better than ChatGPT, such as GPT-5. And here's a visual comparison showing that our predictions are highly aligned with the ground truth. Okay, so TissueLab can also perform the object counting in pathology images. For example, if the user asks, like, help me to count the number of positive lymph nodes, the agent will understand that, well, to do this task, we will need to classify the patches and classify what are the lymph nodes, how many lymph nodes are they, and then we will need to classify the tumor and try to understand whether the tumor is within the lymph node. If within the lymph node, we should consider that lymph node is positive. So we tested this agent workflow generated by our system across many slides. Actually, if I remember correctly, the experiment comes with over 370 slides of lymph node the tumor lymph node metastasis slides. And we found that TissueLab agent achieved a super high accuracy with an average accuracy of 0.92, and it's much better than GPT-5. Oops. Yep. So the beauty of the agent model, our agent system, is the trustworthy. Well, GPT-5 can give you an answer, but you don't actually know to what extent the GPT-5 gives you the answer. And it is really a black box to know to what extent GPT was able to tell this is a positive or not. But we not only give you an answer, we also highlight the trustworthy. We help you to visualize and verify the result in our platform. And if you think it goes wrong, you will immediately know when and how it gets wrong. And you may be able to improve it through the active learning. And so TissueLab can also know when to use online diagnosis criteria. For example, if the user asks, like, what is the diagnosis of lymph node? It is a macrometastasis, micrometastasis, or isolated tumor cell. Well, so the workflow agent will understand that to answer this question, answer this definition, we need to look up online criteria. It will look up the AJCC criteria and integrate it into the workflow and apply to the image. And the final output for this instance will be micrometastasis. And of course, all these steps are fully automated. And not surprisingly, TissueLab wins the race a lot. Other models just failed on this task because it required both the accurate image analysis as well as the diagnostics reasoning. Well, so the beauty of our platform is just not only work for pathology, it also perform well, and it also support other type of medical imaging. For example, it can evaluate the CT scan using the online scoring systems. The agent will search the domain knowledge for scoring and identify a appropriate model, applies it, and generate the output automatically. We found that TissueLab performs much better than GPT-5 and domain expert model such as LavaMed across 14 types of CT analysis tasks. TissueLab can also handle the high dimensional analysis. For example, if you are asking this question, like, does this 3D CT scan suggest fatty liver? The agent will look up criteria, apply segmentation, and output diagnosis. And noting that even our system is outperforming the latest expert model, M3D. TissueLab can even analyze time series 3D cardiac scans or 4D data. For example, if you ask question like, does this scan indicate myocardial hypertrophy? And which is a very challenging task, but TissueLab can still perform better than our competitors. So with so much cool things showed, our team built TissueLab based on two principles. So first, we believe instead of relying on vision language models such as GPT-5, many medical image analysis tasks should be better addressed by breaking them down into key steps that can be handled through a well-designed pipeline. And the second principle is that to solve this pipeline, an agentic AI system can auto-build such pipeline from the user queries that are transparent, adjustable, and explainable. So traditionally, make analogy, if a doctor asks a computational scientist such question, the analysis may take 3 to 6 months. But with TissueLab, the same query can be answered in less than an hour and can be further improved in less than 10 seconds on future iterations. And with more interaction with the platform, TissueLab will gain more knowledge and get smarter and smarter over the time. And that is how we, as a human expert, co-evolve with the AI. And with the platform, we can greatly accelerate both scientific discovery and clinical practice. But what if there's no suitable tool exists in the factory? For example, we want to classify tumor cells for this column image, but there's no tumor cell classifier in our factory. Well, TissueLab can also support human-in-the-loop active learning. For example, this is an image from the 10x genomics. So as a clinician, you can directly annotate the data, and within the 30 minutes, the model performance will improve dramatically. In this example, it aligns closely with the ground truth derived from the spatial transcriptomics, jumping the accuracy initially from 5.3% to 95%. And as you can see that the model over the iteration with human-in-the-loop active learning, it will get smarter and smarter. So immediately, no matter how, you can still quickly establish a classifier to adapt to your own question. And so that follows our principle. If an expert model is suboptimal, you can definitely build a better model on the fly by either researchers or clinicians using the active learning strategy on our existing foundation model. So you can just simply fine-tune the foundation model to solve the task efficiently. And secondly, researchers can upload the fine-tuned classifier based off the existing foundation model to the TissueLab community so other people can reuse it. So that's the power of the community value. And lastly, TissueLab can also handle the multi-model data. For example, when both H&E slides and spatial transcriptomics data are available, the system will automatically check which data exist and propose a reasonable pipeline to solve the question. So if the question in this case is how many glomeruli are in this kidney tissue, TissueLab will generate and execute the pipeline by leveraging the both data modality. And here the output will be 126 glomeruli. And of course, every single step is well documented, all the way from segmentation, cell classification, annotation, and clinician, they can easily validate every single step. And if the performance is suboptimal, we will be able to understand what single step is performing is not performing well, and we will be able to fix it. Of course, comparing to GPT-5, which cannot provide a usable answer, TissueLab can produce results very close to the ground truth, which is 128. And that is actually one of the important steps toward advancing the analysis of the kidney, such as glomerulosclerosis. And with all that cool functions, I guess it's time for the demo. Let's take a look at TissueLab in action. Okay, cool. So right now, TissueLab is a fully open source and available through online platform. It is available on GitHub and our website. We also provide installer for Windows, Mac, and Linux app. And with TissueLab, we conclude that a pipeline of expert tools is much more reliable than end-to-end deep black box vision language models such as GPT-5. And that pipeline can be generated and executed automatically with TissueLab. And TissueLab community and co-evolving agentic AI can learn from the experts and can make the entire system smarter and smarter over the time. TissueLab can eventually greatly accelerate the both research and clinical practice. With TissueLab, we envisioning that everyone can contribute and collaborate an expert model and tool on this open source platform. And such open source community can gather experts to crowdsource annotation, model building, and sharing experiences. It's just like Minecraft or Roblox. TissueLab sets the foundation, we hope, of laboratory intelligence, accelerating hypothesis-driven scientific discovery, and eventually enables the programmable cloud laboratory. So since we released the TissueLab around October last year, it has been 4 months. So far, it has been widely used by multiple pharma, university, and researchers internationally. We have so far within TissueLab, there are more than 300 registered users, runs over 3,700 total workflows, and they are approaching 1,000 total downloads. And we hope TissueLab community can further benefit the entire medical imaging research community in the near future more. And finally, here's my understanding of the large language model-driven agentic AI system. Large language model is powerful. It can solve a lot of things. But as a human, we're just more than our brains. And that's the reason why we are building TissueLab and hopefully reshape the future of medical image analysis. Yeah, so thank you very much for listening to my talk. Previous work has been published at Nature Medicine and Nature Biomedical Engineering. TissueLab is published as a preprint, and software are currently available to be downloaded and used online. So we're also going to have an even more smarter agentic AI system. We call the TissueLab Pro, which are able to learn the clinician's behavior over the time and eventually act as a real clinician to solve the medical image tasks. So please stay tuned. And lastly, I would like to thank you for my audience, for the moderator, and for my fantastic lab members, engineers, and developers. So thank you very much, and happy to take any questions. Thank you.
Thank you so much for this really great presentation and the amazing work that you're doing. Just to remind our attendees that you can use the Q&A feature to post any questions you have for our speaker. And while folks are doing that, I can go ahead and get us started. When thinking about building an agentic framework for comprehensive medical imaging, what types of safeguards do we need to ensure generalizability, recognizing that we don't necessarily have enough data from all types of diverse patient populations, or maybe that health systems don't all have the same state-of-the-art capturing devices and infrastructure?
Yeah, so that's a great question. So the question is about how do we safeguard the trustworthy and safety, and how do we able to generalize those images that are potentially out of the distribution? Yeah, so I think I would like to answer this question by redefining what is the machine learning and what is the future of the machine learning. So over the past 30 years, our machine learning are primarily based on training massive amount of imaging and data, for example, through the ImageNet, and then apply to a small amount of testing samples. And the training and testing paradigm in the past 30 years has been like training on 90% of the data and apply to 10%. And so often the time we want to explore the robustness of the model on an external data set to see the performance. Well, the agentic AI that I am thinking that we are developing is the other way around. We're proposing a new paradigm. We're not doing the machine learning, we're doing the machine perception. We believe the future of the AI should be able to learn like a real human. Think about that. The recent pathology foundation model has been trained on over 3 million of whole slide images and still cannot replace clinicians on those simple tasks. The performance is great. It's like 95%, but it is not 100%. And it is not able to answer you the real questions. And well, think about the other way around. A pathologist to become expert, they only need to learn about 5,000 images to become an expert. So why human doesn't have to learn that many of images to become expert, but machine still have to learn a lot, still cannot compete with human. Similarly, as a human, we can easily learn how to drive vehicle in 30 hours. On average, people can learn how to drive a car within 17 hours, to be honest. But Tesla Autopilot, they have been trained on over billions of video clips, and it still can make mistakes often the time. So we believe the next generation, the next paradigm of machine learning and AI should be learn from the small sample of data and to understand how to solve the problem in a way the same as a human thinking the process, and then be able to adapt to the rest of the 90% of the testing samples. Agentic AI system offers this opportunity. In this case, we're not trying to learn the distribution, the underlying distribution of the images. We're trying to learn how do we solve the problems by using the right tools. And that strategy and that skill set doesn't have to be learned from over 3 million of whole slide images. We can just learn the strategy within those hundreds images and to solve it. Because of this nature of design, the machine learning, or I call it machine perception, we believe that can greatly let the machine, let the system, let the AI system to understand to what extent we can solve this type of problem, and to what extent we are not guaranteed to solve this problem. To what extent we believe this testing image is within our distribution to solve it. To what extent we believe these images hasn't been really think or train in our training phase, and we should invoke human expert to co-design that decision-making process. So we think agentic AI, the way I think, is different from the past machine learning, and hopefully that can enable the future of the research and scientific discovery.
Great. We have a question. One of our attendees said this was a fascinating talk and they already downloaded Tissue Lab during the talk. I'm curious how scalable this is as we improve modalities and additional data layers. For example, as we have spatial transcriptomics along with spatial lipidomics and proteomics, will this tool be able to integrate these types of data with variable degrees of resolution?
Definitely. So the question is about how tissue lab can potentially support different data modalities such as spatial omics or spatial proteomics. For example, spatial proteomics is if it's a codex platform, it is multiplex immunofluorescence. It's just similar to RGB image, but it's a 40 channel instead, right? So it all depends on whether we have the appropriate tool in our factory. And indeed, in our tissue lab community, in our factory, we do comes with the spatial omics softwares or tools. And every single tool has its well-documented description. So when you start feeding the system with spatial omics image and with your questions, we will be able to answer your questions. We will be able to understand your question and find that appropriate tool from those factory to answer your question. We help you to assemble those tools into a workflow. Yes. So in that sense, if we don't have that appropriate tool, then we probably cannot solve the problem. But the beauty of tissue lab but that's also the beauty of tissue lab. Tissue lab is not a fixed factory set. It is a ecosystem where as a user, you can not only use those tools, but also you can upload your own tools into our factory and you can define what these tools can be used for and other people can reuse it. So that's the beauty of tissue lab. And yes, eventually it can help you to answer all the potential questions beyond the regular pathology and radiology images.
Another question is, for a traditional human-only pathology lab, how easy is it to use your open source tissue lab app? Do they need to hire a data scientist to operate and debug or retrain to find how close to the ground truth? What is the learning curve and how long or how much does it take for people to comfortably using?
Yeah, so that's a great question. Yes. So we've been trying to integrate tissue lab in our department, primarily used for research setting. And we found that most of the time, to answer your question directly, in short, in theory, in the future, you don't need a data scientist. Pathologists can be the data scientist with a tissue lab. So that's our ultimate goal. But in real practice, we often find difficulty of pathologists to interact with our system because the system is getting bigger and bigger over the time. And we often found that our users are not quite sure how to ask the question appropriately. Well, this is actually also our limitation of how to design a interface that is more user-friendly. So we're thinking about how to reinventing the UI from Nokia to iPhone. So that's our plan in the future. Yeah, hopefully to make it more friendly. And down the road, ultimately, clinicians, they can be the data scientists themselves to solve the questions without writing any single lines of code. That's our hope.
Great. Could you speak a bit about what information the orchestrator of the system is leveraging about the available tools in order to devise a plan for answering the query? Where does the information come from? For example, the user, or is it auto-extracted from somewhere?
So I'm trying to look up the question. I'm not quite entirely sure. Sorry, could you repeat the question?
Sure. I think the question might be actually similar to the previous question in terms of how easy it is to use the app. And here, the question talks about what information is all needed before somebody can use the app, and do they need to have a plan for answering a query?
Yeah, so I would imagining clinicians or researchers start using the tissue lab will require at least have an initial research goal. Yeah, like what do they want to achieve? Do they want to compute or measure some quantitative measurements of this cohort of data? If so, they will have to try to import these data into tissue lab, either through our local app or upload it online, and then start asking questions regarding that cohort. Yes.
Another question is about when you develop this AI-based work for the initial phase of model development, did you consider input variables relevant to outcomes first with traditional statistical modeling, or do you recommend just throwing all possible input variables and then AI will figure out the most significant risk factors of the targeted outcomes?
Yeah, so that's a great question. So tissue lab can solve two type of things. First is given the existing diagnosis criteria, we help you to assemble a workflow that is aligned with the existing how other people been solving the similar question before. So we're in this stage, we're not innovating anything. We're just trying to re-implementing that workflow that other people has done in the past. But at the same time, Tissue Lab is also the platform to help you accelerate the scientific discovery. Often the time, like we, I'm just making an example. Nobody know how the cluster of lymph node will play the role in melanoma until in 2020. People in Nature published an article describing that the tertiary lymphoid structure, basically a cluster of lymph nodes, is actually indicating a better treatment outcome for the melanoma. And that knowledge scientific discovery hasn't been done in the past, hasn't been systematically summarized. And we believe Tissue Lab can be able to also discovering the new potential biomarkers that is associated within your cohort and try to find a significant biomarker that correlating with either survival diagnosis or therapeutic escape. Yeah, so that's the hope. And we do believe, and actually in our experiment, we do found that Tissue Lab can design and generate a new biomarker that nobody has really developed in the past. Yes.
One of our other questions is might be a little bit more specific. Have you tried to use GPT-5.2 and Gemini Pro 3 instead of GPT-4o in Tissue Lab after segmentation? Would it be more accurate or precise? Or does using smaller LLM work after the segmentation? If so, it can be possibly done without connecting to the cloud on PC or even mobile devices. And if that were true, how far can it be?
Yeah, so that's a great question. That's a perfect question for me to answer. To what extent does the language model be used in this agent AI workflow? Well, so agent AI cannot be done without a language model, without underlying language model. It is like an engine or the wheel of the vehicle. Yeah, so the language model should be smart enough to understand every single documentation of the tool within the factory. So the language model can then understand how to appropriately invoke such tools to assemble in their workflow and solve the problem. To answer the first part of the question, have we tried using GPT 5.2 or better Gemini Pro version to solve the segmentation problem? If it's just asking the GPT to solve the problem without Tissue Lab, well, we tried that. It performed really bad because they do not have the access to our carefully created factory with all those expert tools. All those GPT 5.2 and Gemini, they are just calling OpenCV, write a simple Python code and generate the answer, which is not correct. So to answer the second part of the question, have we also tried using smaller language model? We haven't, to be honest. But eventually, I think this is very important because in the hospital, in the healthcare setting, often the time, the question comes with the PHI information, basically the privacy information about patient. And it might be more complicated to ask a language model hosted on the cloud. So yeah, we hope that a local smaller language model can also have the same capability to answer the question. But so far, we're facing some limitation about those smaller models. Actually, we do find even GPT-5 cannot answer some complex question. Only GPT 5.2 can really answer it. When I say answer, I mean those GPT model to understand the user query and to call the appropriate tool, assemble them into a workflow. Yeah, so the power of the language model does affect the performance a lot. Yeah.
A lot of people are talking about how excited they are to try Tissue Lab. A question specifically is whether Tissue Lab would be incorporated into a local Linux system powered by private GPUs and be able to access the data. For a fully designed pipe, how do you better benchmark, compare different models, and compare performance in large scale?
Right. So to answer the first part of the question, Tissue Lab right now is fully open source and everybody can just clone the Git repository and re-implement it on a private server or GPU. and to access their own private data. Alternatively, our web platform is a much easier way for any new user to use it without installation. And for a full design pipeline to benchmarking the different models, such as different tile encoder, well, I think, yeah, that is a lot of effort of the work. Yeah, so down the road, we definitely want to benchmark it, and especially to see which model is the most suitable for what type of task. And most importantly, that's also highlighting the value of the ecosystem that we're trying to build. For example, if you find out that the pathology foundation model A works well on your own cases in colon, but doesn't work well on your breast cancer cases, the knowledge, the skill set that you're trying to get will be also, with your permission, uploaded on our cloud. So TeachLab Brain will try to understand in the future when other people trying to solve the problem within the column, we better use the model A rather than model B. So that experiences are going to be shared across the entire community, and everybody will benefit from this crowdsourced usage of the TeachLab.
And speaking about future steps, how often do you update TissueLab? And are you planning to submit for FDA or some other regulatory body approval for future clinical use?
Yes, eventually we definitely will. TissueLab is our long-term goal to potentially, I hope, to revolutionize the healthcare industry. But getting an FDA clearance is of course, it's not a trivial task. Actually, a recent survey found that over the past 5 or 10 years, there were like over 1,000 medical devices being approved by FDA, medical image device. 97% of them are from radiology, and only 3 pathology devices has been approved in FDA. So that's a very, very tough. Yeah. We hope down the road we will be able to get FDA clearance. Yes. And how often do we update the TissueLab software? Well, TissueLab is incubated within academic laboratory, and all our fantastic engineers are actually graduate students. So definitely we're not able to iterate this software as fast as in industry level, but down the road we may seek for collaboration or even spin off a company to accelerate to boost this development. Yes.
Great. Another question has to do with all this innovative research you've been doing. What has been your biggest frustration or something where if you knew ahead of time you would have done things differently?
Yeah, that's an interesting question. I'm trying to understand the question. The biggest frustration, like basically asking like what is the task that only TissueLab can do and other people cannot do? Yeah. Well, I would say a lot, right? Like a lot of complex questions, and there's no end-to-end model can solve that problem. And often the time we need to hire someone, data scientist, postdoc to develop a workflow to answer this question. But with TissueLab, we can do that theoretically, automatically. Yes.
Mhm. Great. And more comments about what a great presentation this was and people looking forward to actually using the app. Um, I want to really thank you so much for this great presentation. I think you've inspired a lot of us to download TissueLab and explore more. Thank you for this really innovative work. I want to remind our attendees that this session is being recorded and should be made available on our YouTube channel within a week or so. Our next webinar will be Thursday, March 12th, where we have Dr. Amir Rahmani, who is the director of the UC Irvine Institute for Future Health, who will be talking about wearables, agentic AI, and living labs, the future of health innovation. So with that, Dr. Huang, thank you again so much, and thank you all for attending today's webinar.
Thank you for having me. Yeah, my pleasure.